Okay, diffusion is something that you're familiar with, just from your experience of being alive, which is the movement of particles from areas of high concentration to low concentration. So what does that mean? It means if someone opens their McDonald's French fries in the corner of the room, eventually everybody can smell them. So the particles that are causing the smell are diffusing through the room from the area of high concentration, which is around the French fries, to the other areas until they're evenly distributed. Another example is when you add food coloring to water, it diffuses through the water. So fluids diffuse because of the kinetic molecular theory, essentially. Okay, so if a sample of H2 and a sample of N2 are in separate balloons, and they're both at the same temperature, which has more kinetic energy? Lucas? Yes, they have the same kinetic energy. This is something that you can plan to see later in an environment that matters. So they have the same kinetic energy because they're at the same temperature. Okay. However, this is our follow-up question. Which one has higher average velocity? So in other words, which will diffuse faster? Maya? Good. H2. Okay, and this is because of an equation that you guys learned in physics for kinetic energy, which is, Maritza? Yes, 1/2 mv squared. Okay, so even two things that have the same kinetic energy can have different velocities if they have different masses. Okay, so maybe a slightly easier version of this is thinking of momentum, which I think you learned about last year. So if you think about like a Civic or something, a Honda Civic. Okay, I think momentum was capital P. I can't remember, but that's what I mean for mean here. So momentum is mass times velocity. So if you think about something like a car, it has a pretty big mass. And if it's creeping along really slowly, let's say it's a Prius, and it's moving less than 5 miles per hour silently through a parking lot towards a target, it has a tiny velocity, then it has a certain momentum. Similarly, a baseball could have the same exact momentum, even though it has a much smaller mass, if it has a much greater velocity. So there's kind of that inverse relationship. So the same is true for masses and velocities with gases that have the same kinetic energy. So if we were to summarize that, we would say at the same temp, particles with lower mass, and we can think of that as molar mass on the periodic table, particles with lower mass will be traveling at a higher velocity than heavier particles. At the same temperature. That's when we can make that conclusion, because then they have the same kinetic energy. Okay, so here's our equation, 1/2 mv squared. So this is just a follow-up to see if you're getting it. Which would diffuse faster, nitrogen or neon? If you look at the periodic table, neon is 20.18. Some of you already know nitrogen. Ayush, 14.01. Good. Okay, so which of these would be diffusing faster, nitrogen or neon? Milan? Neon is correct. Okay, why? Maggie? Good. Okay, Hunkle breath. So nitrogen is actually N2, and each particle would actually have a mass of 28.02 AMUs, every molecule. Okay, but we can think of it in grams per mole also. Okay, yeah, that's a little tricky, but the nitrogen would diffuse more slowly because each molecule, like individual particle, has a larger mass. Okay, it's easy to compare two gases at the same temp. Why is it harder when they're at different temperatures? Caddy? Because their kinetic energies are not equal, and then you have multiple things that vary, and it's possible to compare, but it would just be more complicated, so we're only going to compare at the same temperature. Okay, a fusion is similar, but it's actually the process of a gas escaping from a tiny hole. Can anybody think of a situation where you would have a tiny hole in a container? Sean? Yes, like a balloon. Good. So balloons have tiny holes in them, which is why they get smaller with time. So we're going to draw a balloon here. Oh, I was going to show you a demo for diffusion. I'll show you in a minute. Okay, so we have a tiny balloon here. Let's say that one of them has hydrogen in it. It's our explosive balloon, and one has, I was going to say air. Let's say nitrogen. Okay, so if you think about how these balloons have tiny holes in them, and there's a gas that occasionally will collide with that hole and escape, which of them is going to escape more frequently from that hole? Will it be H2 or N2? Shreya? Good, H2. Okay, because it is a smaller mass, has a smaller mass, therefore it has a higher velocity, so it will more often hit the hole and escape. So if this is day 0, then on day 3 or whatever, however long later you come, will they both be smaller? Annika, yes, they'll both be smaller, but the H2 will be more smaller, so to speak. It will be smaller, okay? Because more of these particles have collided with the holes and escaped because it's lighter, it's moving faster. Okay, so that's a fusion. I do want to go back and do a diffusion demo for you guys, and this is the premise of this demo, is you have this tube, here, you have a tube like this, and it's got these 2 cotton balls on the end, and they soak them in these noxious, gross gases. Okay, well, they're liquids, but they're really volatile, which means that they evaporate easily. Good. Okay, so on one side you have HCl, and on the other side you have NH3. And just to give you a sense of what we're dealing with, the molar masses of these are about 36 grams per mole for HCl and 17 for ammonia. Okay, so let's watch this demo and see what happens when these get into this.
Well, hopefully you've started to observe some white cloudy material forming here. It's a solid. It's swirling around as a smoke suspended in the air there. What is it? How do you explain the formation of the white solid? How do you explain where it forms?
That's basically all he says. I just love that the whole video is just him asking questions. And I wonder if I asked you questions with a British accent, if you would learn better from me. His 2 questions. What is it? Why does it form there? Okay, so what is it? It's basically, I'll give you a hint that it's a synthesis reaction. You have 2 gases, in this case, combining. So when you put these together, you get... Okay, what type of compound is often a white solid at room temperature? Preeti? Ionic compounds, good. And what is the name of this ionic compound? Rhea? Ammonium chloride. Good. Okay, so it's the solid is forming right here. It's kind of swirling around. It's white though. Okay, so the question then is, what is on, like why does it form there? It has to do with how fast the gases are traveling. So what is the identity of the gas on this cotton ball? Lizzie? Yeah, good. This cotton ball has HCl on it. Okay, and how do we know that? Because HCl is heavier, so it travels more slowly. So in the same amount of time, it does not travel as far as the ammonia does, which is substantially lighter. Okay, so the ammonia is over here on this cotton ball. Okay, forming a white ionic compound together, ammonium chloride. Okay. That's still recording, thank goodness. All right, So the last thing we have to talk about here is that there is a mathematical equation for this, which is called Graham's law, and essentially it will give you a ratio of rates. So the way to interpret that is if you were to plug in these numbers, which we'll go over in a second, and get 2, you would say A effuses twice as fast as B. So if you have a number over here that's greater than 1, that means that A is the thing that's effusing faster. Okay? Conversely, let's say that you plug in your numbers, and I think if you can think about it in advance, it's helpful to plug in your number so you get a whole number on the left, which means that having a larger number for B than for A. Okay? Conversely, if you got 1/2 or 1/3, you would say A effuses at 1/2 the rate of B. Okay? It's also completely legitimate to interpret it that way, but you might be a little more likely to get confused. So let's do an example. At room temp, which molecule travels faster, nitrogen or oxygen? Jaden? Nitrogen. Good. So how much faster? Okay, so we need our equation. Again, I want the thing that is faster to be A, so that this ratio is greater than 1, so it's easier to interpret. So I'm going to make A nitrogen. Okay, so I'm going to say the rate of nitrogen compared to the rate of oxygen is equal to, and we can do a square root of the whole right side. You understand that math stuff. Okay, molar mass of B. So please be aware that they flip here, okay? B goes on the top on the other side. Okay, so we're going to say Hunkelbrief 32.00 divided by 28.02. Okay, and we get, I don't have to calculate it because I remember this because this isn't my first time doing this. Okay, 1.069. The way you would interpret that is nitrogen effuses 1.069 times faster than oxygen. Okay, if you had done it the opposite way, the reciprocal of this is something like 0.9857. I don't remember exactly. So it's a little harder to interpret that. You would say oxygen, because you would have flipped it, effuses 0.9857 times as fast as nitrogen, which to me feels harder to think about. So, but it's possible. You can also flip it. If you accidentally plug it in the wrong way, you can find the reciprocal, raise it to -1, and you'll get the opposite. Okay, here's a similar problem, except we have a different unknown. So which pure gas is the question, okay, is faster than neon? So if the 3.16 times faster, so we're going to put 3.16 over here. That's the ratio. So the question is the unknown lighter than or heavier than neon? Okay, so I couldn't think of a name. Okay, good. Yeah, it's going to be lighter than neon because it's faster than neon. Okay, so what we need to do then, let me erase that, is say which one is neon. So is A or B neon? Emily Lee? Yeah, good. We want our unknown to be the one that's faster on top, so the neon is going to be the slower one that's going to be in the bottom. So B is going to be neon. Okay, so let's think about that when we plug this in. So we're going to say the molar mass of neon is 20.18. Okay, and then our unknown's molar mass, we're going to call X. Okay, if you solve this out, you get 2.02 grams per mole, which you'll find is not on the PR table. So, Emily Takara, good, hydrogen. Okay, another way you can think about that is if, like I think I've done problems in the past where the molar mass is both the molar mass of a gas but also of a pure element, that's a solid. So it has to be the one that's a gas if those are your options, okay? Because we're talking about a fusion of gases. Okay, that's gut.